Okay, so today will be the seventh and last lecture of this series on instantons. And I feel that we've covered some distance, but there's a lot more to cover. We've essentially now gone through all the items on this list that you can see over here. So we started out with particle mechanics, and in that context did the path integral, went to imaginary time, etc. And the last thing that we did, that is in our previous lecture, we talked about gauge theories, in which basically you have a compensating field. So when you make a local gauge transformation, you can subsume the effects of that transformation by introducing a new field. And we will continue that discussion now. We will today get to instantons in a Yang-Mills gauge theory. And this will call for using the mathematical machinery that I had indicated, that is the machinery of differential forms. Now, that will be essential over here. Instantons, first of all, let me define them. An instanton is a configuration of a Yang-Mills field that solves the equation of motion and has finite action. Now, in the particle mechanics example that we took earlier, the equation of motion, which we got by varying the Lagrangian, it's just the Euler-Lagrange equation, was easy to solve. The solution was hyperbolic tan. Now, in the case of Yang-Mills gauge theories, it's going to be different, but it's going to be similar in the sense that you go from one vacuum to another. So an instanton is something that takes you from one vacuum to another vacuum, both of them, of course, being degenerate, having the same energy. And we will see that in the case of Yang-Mills gauge theories, there can be an infinite number of vacua. Where these vacua will come from, we'll talk about that. Okay, so I will need differential forms, and I'll briefly review what I'd mentioned last time. So this whole subject can be attacked, of course, without using differential forms, but it's much cleaner, nicer, and in the few minutes that we have today for the lecture, this can be done very cleanly and quickly if we use this language. All right, so here we have just an ordinary field component, A mu. We multiply it by dx mu. This is a differential. And now you see there are no indices left because we've contracted on mu, which goes over 0, 1, 2, 3, or however many dimensions there are. The good thing about A is that it doesn't have any indices. And when you do a coordinate transformation, when you go from one point to the other, A doesn't change. So you can see over here that A is just equal to A itself, but written differently because there is a transformation that comes over here through this chain rule. Similarly, there's a two form, which is a one form wedge with another one form. And we can make three forms, any number of forms, up till 4 in 4 dimensions. Now, these are antisymmetric under multiplication. So this is the rule by which forms are multiplied together. Again, this over here is invariant under change. Under the change, x goes to x prime. And the nice thing about this is that this A mu prime or this A mu over here has to be anti-symmetric. See, if it had a symmetric component, that would be then multiplied by something which is anti-symmetric, and that would give 0. So this, of course, has to be anti-symmetric. I also mentioned the exterior derivative, and I hope that you've read up something since that time. So what an exterior derivative does is it raises the form, it takes a P form and makes it a P plus 1 form. So D acting on this 2 form A, here's the 2 form A mu, dx nu. Well, what it does is it differentiates with respect to another index, rho in this case, and puts a wedge over here. And so now we have a 3 form from a 2 form. So D raises the form index by 1. Now it's very easy to prove that if you apply D twice on anything, you will get 0. And that tells you D squared is 0. Basically, it is that if you apply D over here, then you would have, let's say, D sigma dx sigma, and then you would have because of the commutation of partial derivatives, dx sigma and d rho, they commute with each other. Therefore, whatever form is over here, if it is of the type, rather I should say, d times something, well then d acting on that will give you 0. This is a very useful fact that we'll use again and again in what's going to happen now. This is the Poincare lemma, that if dH is equal to 0, then H is equal to dk. Now, it's pretty obvious that if you take dH, well, that's d squared k, that's 0, but going the other way needs some proof. Of course, we're not going to do any proofs. And finally, we will need this rule of integration, that if you integrate a form which is of the type dA over a manifold, then that's equal to integrating A over the boundary of that manifold. This is Gauss's law. It's also Green's theorem. It's the fundamental theorem of calculus. Okay, so now let's come down to business. In a gauge theory, we have the tensor F mu nu, and we're used to it from electromagnetism, where F mu nu is equal to d mu a nu minus d nu a mu. And what we want to do is construct a 2 form that mirrors the F mu nu that we already know from electromagnetism. And electromagnetism is a very simple theory because it is an abelian theory. What we're going to need this 2 form for is a Yang-Mills theory, and we already have one thing, which is the gauge potential. From the gauge potential, we make the 1 form, and now the question is, how do you make a 2 form? F has to be a 2 form. Okay? Just to remind you, we do our gauge transformations using this matrix U, which is different at different points in space. Now, this is a matrix which belongs to some gauge group. It could be SU2, it could be SU3, whatever. And it's a unitary matrix. So U dagger U is 1 at every point in space. This is the U that transforms the A, and this compensating field A mu is put in the covariant derivative. So the covariant derivative we defined as this. Now, let's remember that U is a function. Well, of course, it's a matrix, but it's a matrix of functions. So it's a zero form. Therefore, if I take du, well, that's a one form. And how do you make the one form? Well, as I said earlier, d mu u dx mu, that's the rule by which d operates upon a function. Okay, so we have this du as a one form. We're going to need an identity again and again, which is that u dagger u is 1. Therefore, d on that has to be 1 because it's a partial derivative. And so d acting on 1 will give you 0. Now, if you differentiate this, then you have du dagger u and then u dagger du. And remember that I could take this d across over here without any change of sign because u is just a function. A matrix, but it's a function. Okay, so what is it that we want? We want a Lagrangian which is a scalar under the transformation phi of x goes to u acting on phi of x. So we want the covariant derivative to transform like this. So when phi goes to u phi, we want d mu phi to go to u d mu phi. And of course, it's Hermitian conjugate, which you would like to transform in this way. You want this so that when you take this quantity, d mu phi dagger d mu phi, you want it to become itself. And it can become itself because if d mu dagger transforms like this and d mu transforms like this, then the whole transforms like this, and u dagger u is equal to 1, and so it becomes itself. So then that makes the kinetic part of the Lagrangian invariant. But A has to transform, and this will be true only if A mu transforms like this. Now, it's a matter of actually doing a calculation by hand, and it takes 5 minutes. So in other words, you make phi go to u phi, you make this d mu, which is up over here. So in this phi, you will put you'll put u phi, and in this a mu, you will put this thing over here, and it is only in that situation that that the kinetic part of the Lagrangian will remain invariant. Okay, so if you accept that, let's look over here. So look at this transformation of A mu. I'm going to multiply this side and this side with dx mu, with the differential dx mu. So then this over here becomes a one form. And now this dx mu, remember I can take it past this function. This u is a matrix function. And so this is also a one form. And similarly over here. So then by multiplying by dx mu, I've gotten rid of all the indices. So this now looks much nicer. It is also it's not only looking nicer, it is nicer, although it's the same as what you saw earlier. So A has gone into this. Now you see there was an I over here, iota. And the way it is done, people like Polyakov and Witten and all these people, what they do is they define a new a new gauge potential, A mu. They hide the I by putting it in the new A mu. And so that's very nice because instead of having I's floating all over the place, you get the covariant derivative is just D plus A. So this is now a one-form operator. It's an operator, remember. D is an operator, but it's a one-form operator. And by the way, if you take this, if you square this, you'll find something very nice and amusing. But I won't do that over here. So now, what will be the next step? We've made some progress. So how do you go about this? How do you go about trying to make the two-form F? Okay, the easiest thing is to multiply two one-forms together, and that makes it a two-form. So make all the possible two forms you can construct from A and dA, the operator small d, which acts on something, and then you can add them together. Now, there's only two ways that you can do it. You can multiply A by itself, or you could have D acting on A. Yeah. Well, let's first look at A into A. All right, then when A becomes this, then this is a no-brainer. A squared becomes A into A. I've transformed both of them equally. Okay, so now let's start multiplying them together. So UA, U dagger, U, A, U dagger. So that gives you UA squared, U dagger. Then take this into that, and that gives you UA du dagger. So this du dagger is here, and then take this thing, which is this, and finally take u du dagger, u du dagger. So it's pretty straightforward there. Okay, now let me use this fact that u dagger u is equal to 1, which means that we have this relationship here. And now let's see how we can apply that here. Nothing to do over here, nothing to do over here. But look over here, there's d u dagger u. I'm going to replace that with du a. And now there's a u dagger u that comes in, which is equal to 1. And finally over here, I'm going to do exactly the same here. Du dagger u, okay? These two terms. Now, you can see over here that this is equal to minus du dagger u. And so u dagger u is equal to 1, and so that's equal to that. Okay, now we've dealt with a squared. Now let me look at dA. Okay, so A, of course, goes like this. So how does dA go? Well, let's apply D to this thing over here, U A dagger U. What do we get? Okay, so D acting on U gives you du. D, okay, now there's AU dagger, of course, left over. Then then D has to go across over here. So it's, and so that's DAU dagger. Here we have DU dagger, but then when D crosses this and acts on this, you get 0. So 3 terms over here.
It's just the Leibniz rule again.
It's just the Leibniz rule that we are applying again and again. And now notice over here. If I add dA to a squared, well, this will remain, but notice that this over here minus du au dagger cancels with this over here, and this will cancel with this over here, which means that if I take the sum of dA plus a squared, by the way, I'm not using this wedge anymore because it is too cumbersome. Every time, I should have said this earlier, that for example, over here, this is a wedge A, but you get tired of writing it, so it's just nicer to write it A. One just has to remember what is a one form and what is a component. A component will always have an index on it, so there's no possibility of a confusion. Okay, so we are here. Here is the field strength tensor for a Yang-Mills theory written in an absolutely basic, simple form, no indices, nothing. F is dA plus AA. Right, and then how does it transform? Well, when A undergoes this transformation, then see what happens to it. So F will go to so we have F is dA, so apply dA to here, you'll get this, and then the next one, you'll get this, and so you get UF, U dagger. Now, in electromagnetism, what we have is that when you make a gauge transformation, F doesn't change. The electric and magnetic fields don't change when you make a gauge transformation. Let's say you go to the Coulomb gauge or to the Lorentz gauge or to the light cone gauge or whatever. F doesn't change for electromagnetism, but electromagnetism is an abelian theory. Here there is a change, but it's a covariant change, which means that if I was to take two Fs, so take this F, multiply it by itself, and remember this is a matrix. F is a matrix because A is a matrix. So if I take two A's, A, and I take the trace of that, then by the cyclic property of the trace, a trace of AA will be a scalar. So that's why this thing is so nice. You see, you can almost see it mentally without doing things. UF, U dagger, multiplied by itself. So there'll be UF, U dagger. U dagger, U is 1. And now if you are taking the trace of this, then you can just take U dagger to the beginning. And so this is an invariant. Okay, now we need to look at some properties of F. And now this is something that we have achieved, and so it needs to be celebrated. F is dA plus AA. Okay, this is just a reminder that we're dealing with fields which have got space-time indices and which have got internal indices. So this is the group index A. And this A, if it's an SUN matrix, it will go from 1 up till n squared minus 1. So for QCD, where you have SU3 invariance, you will have A goes from 1 up till 8. There are, remember, 8 gluons, so this is exactly QCD. And now, if you want space-time indices, so this is fine as it is, but suppose you want space-time indices, then what do? Okay, so multiply this over here, this by dx mu. And or just put, sorry, just put A equal to A mu dx mu. Right? I've over here, instead of A, I put A mu dx mu. Here I have two A's, so A mu A nu dx mu dx nu. All right. Now, what is d A mu? It's d nu A mu dx nu. Remember that the rule by which you make d operate on anything, on, in this case, scalar, in this case a zero form, well, it increases it makes the one form into a two form. So you have this two form here, and you have, this I've just written as it is. And now this is antisymmetric. You can just read off what F mu nu is. It's d mu A nu minus d nu A mu plus the commutator. See, here is, you can see there's a commutator involved over here. That's because these A's don't commute with each other. They're matrices. This A is a matrix over here. Right. Now suppose you want group indices. So I've restored the space-time indices over here. Now suppose I want to restore the group indices. So if you write A mu as this, A mu A TA, A is summed over all the group generators from 1 up till n squared minus 1. And these group generators obey this commutation relation. TATB is FABCITC. Then this F mu nu, so just put A mu equal to this in here, and then you see that F mu nu A is equal to this. So now it's completely explicit. Now compare how ugly this is with how beautiful this is. Okay, but of course, we're not just out for beauty, we are out to get a job done. Now, let me take A, the one form A, as this G, where G is a group element which belongs to SUN. So A is equal to G, D, G dagger. So this is a one form. D acts on a function. A function is conjugate. It's a matrix, a matrix function. And of course, this is a unitary matrix. So this is. Now, I claim that if A is equal to this, then F is 0. And this is going to be very important now for what I'm going to do. I'm going to get instantons very fast. When you write A in this form, matrix D, matrix conjugate, Hermitian conjugate, then this thing is called a pure gauge. Now, this needs to be proved. It's easy to prove. So let's take our definition of the two-form field strength tensor F. This is dA plus AA. Let's fit that in. So D acting on G, so acting on G, D, G dagger, and then this thing squared. Okay, so what happens over here? D acts on G, but then when D goes beyond G, you get D squared, so that's 0. So you just get DG, DG dagger. And now here, what are we doing? Here we're using the fact that when you take d of g dagger g, then that's equal to 0. And so you just flip that around. And so look, GG dagger is 1, and so this and this have cancelled. The point is, and this is a very important point, that any A which can be written in this form gives rise to a 0 field strength tensor. F is 0, although A is not 0. Okay. And well, this is almost obvious that in electromagnetism, we're used to two different Fs. One is F mu nu, which is d mu a nu minus d nu a nu. The other is F twiddle, or F tilde, which is called the it's called the conjugate dual. It's called the dual field strength tensor. Okay, so how do you make the dual field strength tensor from the usual one? Well, you multiply by this Levi-Civita tensor U epsilon mu nu rho sigma, and therefore you can make this. You can make an invariant from F and F tilde, and you can write that as F squared. Now, if you take the trace of that, as I explained earlier, you then have an invariant. And that tells us that we can now we can put in our action the trace of F squared. So with the F twiddle F, we've now added a term to the action. Okay, now the action, as we see it normally, is with real time, dt d3x, but now I've gone over to imaginary time, and this is the quantity which, if you minimize, will give you the classical equations of motion. So just as we did in particle mechanics, we have an action. That action has Euler-Lagrange equations as the equations of motion, and we are now set to play the same game. Here is now something important. You see, this integral over here will diverge unless f goes to 0 at infinity. And now if you write d for x in polar coordinates, well, it's the magnitude of x cubed, dr, d omega. So there's a solid angle in 4 dimensions that you need to integrate over. But the important thing is this. Now, if f goes to 0 as 1 over r squared, that means I'll have dr over r, which is logarithmic, which means that it's got to go to 0 slightly faster than 1 over r squared in order to give a finite action. Of course, f has to go to 0, which means that a has to go to g dg dagger. That's the only way that you can keep this action over here finite. Now, here's a bit of manipulation which says that the trace of f squared can be written as this, as d of something. Oh, that's nice, isn't it? If it can be written, if the trace of f squared can be written as d of something, then we will be able to use our integration rule. We'll be able to use Gauss's theorem. Okay, so let's see what happens. Let's see if we are able to prove this or not. And okay, so let's start with, we could start from the left or we could start from the right. Let's start from the right over here. So the right side is the trace of D acting on this, acting on the first, and then acting on the second. When it acts on the first, then we have this, and then, of course, this I've just, D is now acting on A cubed. Okay, let's see what that gives. So D acts on A, gives DA, DA. D acts on DA, gives you 0. And then look at the trace over here. So D acting on A cubed can be written as D acting on A into A squared. So it first acts, so I mean, I've written A cubed as A into A squared, which is, of course, I'm allowed to do. So then this is dA, A squared. And then see, I have a minus sign over here. Why do I have a minus sign? Because D, when it crosses a one form, this is itself a one form, right? When it crosses a one form, you get a minus sign. So that minus sign comes here. And this is ADA squared. The only thing that I need to do now is to work out D of A squared. All this is the same as before, but D of A squared will be A dA into A. So this A squared is to be regarded as A into A. And then when I cross D over, there I get a minus sign, so this becomes plus. Okay, so this now, so it's pretty clear that here this we have traced dA dA and 2dA A squared. Now what happened over here? Remember that this is a trace, and they simply doubled up over here. Okay, so so three of these, I shouldn't have said doubled up. I should have said this, this, and this. That's the 3, that cancels the 3, and then the 2 multiplies what's inside. Okay, now let us look at the right-hand side. At the left-hand side, I'm sorry. So now I have trace of F squared, so trace of F into F. F is dA plus A squared. Multiply this out. dA into dA, which is here. dA into A squared, which is here. And A squared into dA, which is here. And then I have A to the 4th. Now, A to the 4th, I am multiplying 4 one forms together. And let me persuade you that the trace of that has to be 0. Why? Because I can write A to the 4 as A cubed into A. But I can use the trace property and write this as A into A cubed. So trace of A to the 4 is equal to minus trace of A to the 4, which means that the trace of A to the 4 is equal to 0. It's a nice, pretty straightforward thing. But you see, this is the whole beauty of this, that you don't need to do elaborate calculations once you have the language right. And so let's see what this is. So then this is dA, dA, and these two add up. You can switch the positions around because of the trace property. And that's exactly what we had for the right-hand side. So this and this match. Okay. Now we're getting to the real meat of the argument. So in our Lagrangian, we had F dual F trace, and we were integrating over all of space, that is to say R4. But this trace of F squared, we have just proved to be the D, the total, so this is like a total derivative of sorts. So D of this. Okay, but now I can use the fundamental theorem of calculus, or Gauss's theorem, or whatever you want to call it. Take the trace outside, and I have A dA plus 2/3 A cubed. And this is now over the surface which bounds R4. And this is a surface that I can choose. Let me choose that surface to be the sphere S3. So this is a four-dimensional space, and there's a surface which is three-dimensional, and we can make it spherical if we like. Okay, so let's see what happens. Now this dA is equal to F minus A squared. Why? Because F is equal to dA plus F squared. So we have, this is that, and 2/3 A cubed remains where it is. But here, on the surface of, so on S3, which means the bounding surface, we have just argued that for the action to remain finite, the field strength tensor must be 0. So F is equal to 0. So what we have over here, A minus A squared plus 2/3 A cubed. And that's minus 1/3 trace of A cubed on S3. Hence, we have proved that the action is now this thing over here for any matrix in SUN. So whichever Yang-Mills gauge theory you take, whichever n you choose, you will have this thing, you will have the action equal to this. Just to give you an example, let's take SU2. So in that case, G will be the unit matrix and the Pauli matrices. So it's these are the generators. The Pauli matrices are generators of rotations in 3 dimensions. Okay, so G is equal to this. Stick in the Pauli matrices, and this is what you get. Now this has got to have determinant G equal to 1 if it's an SU3, if it's an SU2 matrix. By definition of the special unitary group. So this into that minus this into that has to equal to 1. That says that x1, x2, x3, and I could have called this x4, but we should maybe keep in mind that we're dealing with imaginary time, and so keep it as tau rather than x4. Now that's the group manifold of SU2. And of course, if you take this G and multiply it by its conjugate, you'll get 1. That comes from this condition here. Okay, so that gives you an example. But I could have taken not just this G, but I could have taken G to the n instead. And remember, determinant of
the determinant of a product is the product.
The determinant of the product is the product of the determinant. So this would be determinant of G to the n is also 1. Now these are different n's. They give you the same energy. but they correspond to different vacuum states. And here the whole machinery of homotopy theory can be used, and how to classify these maps. So you see, this is a map. X1, X2, X3, tau. This is a point on the sphere S3, and to that there corresponds this matrix. So you are so with each point on the manifold, on the boundary of the manifold, there corresponds an SUN matrix. Here I took a sphere, but now here is where, you know, a lot of nice mathematics comes in. What if you change the sphere? What if you distort the sphere a little bit? Does it change the value of the action? Answer is no. What if you distort it in some terrible way, but the manifold doesn't cross itself, so you don't create
You don't create holes, and
you don't create holes, and you don't create
You're not creating holes, and you're not creating corners.
yes, you're not creating corners, you're not creating holes. The action doesn't change. So this is what is called a topological invariant. Now, unfortunately, we are not mathematically equipped to go much beyond this, but actually we could do this, but it would take a little bit of time, too much time, more than we have. So for some future discussion, I will just tell you some of the things that we could have talked about. So these are solutions that were got. So the Yang-Mills equation of motion, d mu f mu nu, this is a partial differential equation. It's highly nonlinear. It's nonlinear because you have products of A's, not just two products is fine, but three products and four products. In QCD, we would say this corresponds to the 3 gluon interaction and the 4 gluon interaction. And it would seem as if it's impossible to solve, but some very clever people were able to get a solution for that. And the solitons, the instantons that come out of solving this have their names associated with this. So you have the BPST instanton and so forth. So it is possible to solve, and it's actually not very hard. You have to have the right idea. And basically the way they got it was by saying that F mu nu and F mu nu twiddle have to be the same, and that's a condition that you must have for an instanton to exist. These imaginary time instantons, so we saw that you can choose n to be anything. But what is the instanton? It's a solution of the classical equations of motion that connects one vacuum to another. When we did the particle mechanics case, we saw that it connected the vacuum at minus A to the vacuum at plus A. So you had the hyperbolic tan of tau, basically, A times hyperbolic tan of tau. When tau goes to minus infinity, it goes to minus A. When tau goes to plus infinity, it goes to plus A. So in the same sense, the instanton of Yang-Mills gauge theories takes you from one QCD vacuum to another. In fact, I'll end over here. This Yang-Mills vacuum has an infinite number of vacua. And in fact, you can't say that the vacuum that we do perturbative calculations in, and so people who do part-on model calculations, people who do perturbative QCD, they think that their vacuum is the right vacuum. But that vacuum could be any one of these infinite number of vacua. And in fact, you can show that it is actually wrong to say that there is just one vacuum of QCD, because then this would lead to correlation functions not dying off when separated by space-time, by large distances. So there are lots of implications of this for solving QCD and other Yang-Mills theories, of course. But these are all issues for future discussion. Now, if people want to read about this, there are two very good additional references that I've added over here. One is QFT in a Nutshell by Anthony Z, and the other is this Instantons and Large N by Marino. So that's all for now, and let's hope your interest has been sparked by these lectures. Okay. We're done. Any questions? This is actually, the differential geometry language is abstract and it's good, but it's, when you actually have to solve equations, then you have to come down to the world of indices. So it's good to know both languages. But see, this I was able to do very fast. In just 45 minutes or so, we were able to see that there are topological invariants. That if you, all you have, first of all, you see that the fields have to drop off fast. You need to pick the gauge fields of a particular type only. G, D, G dagger. And then from that comes the notion of topological charge, which is invariant under deformations of your geometry.
So we have this instanton solutions in non-abelian gauge theories, but we don't have in abelian, right? Or like
we did see an example. We saw the O4 instanton, which was for a phi to the fourth theory.
Actually, I was thinking about U1 electromagnetism. So we don't have instanton solution in that.
In ordinary electromagnetism?
Yes, U1 versus SU3 color.
No, for U1, there is no instanton. That's like a sort of a trivial gauge theory.
What about this electroweak model, SU2 cross U1? Do we have
yes,
these
you have instantons there. They are called sphelerons, and they are also classical. They are solutions of the classical field equations for the standard model, and they are responsible for baryon number violation. One thing I should have mentioned is that this theta vacuum that I wrote, it violates parity and time reversal. And so the question is that if you put this term into the action, then why is this term not apparent in our daily life? If it was there, then it would have certain observable consequences. In particular, the neutron should have a dipole moment, which it does not. Okay, but coming back to the standard model, yes, you have baryon number violating classical solutions to the standard model.
Thank you.
They have not been seen, though. I mean, because you actually do a calculation, it turns out that baryon violation happens at super high temperatures. And so while it could have happened at the early stages of the Big Bang, this is not something that has been seen at CERN.
So can we study the instantons of lattice gauge theories? Like, can we see instantons in those formulas?
Actually, lattice gauge theories have instantons in them. So that's basically a way of discretizing continuum quantum field theory. And yes, in fact, instantons have a big role to play in lattice gauge theory.
So what kind of transitions are involved? Because from one vacuum, you are going to another vacuum. So instanton would take you... essentially, we do lattice gauge theory for studying the transitions or the phases of materials or condensed matter. So can we relate that phase transition to what we are studying now, the vacuum decay or the transition of vacuums?
Well, look, there are all sorts of things in lattice gauge theory, and I know very little about it. But you have kinks and vortices and instantons and all kinds of domain walls which exist in lattice. It can be made to exist on the lattice. Okay.